Okay. So there's like 2 more topics in the last bit of this chapter. And then next Monday we'll do functional groups, and that will be it. The first part of this is called Aromatic Compounds. Kind of sounds like things that smell. That's where the name comes from. But in chemistry, that's been expanded to a much broader class of compounds. And the aromatic compounds have these special structures that kind of look like this. They're all rings. And let's take a look at a 6-membered carbon ring. Normally we would call this cyclohexane. But something special happens if it has alternating double bonds all the way around the ring. So instead of single bonds, you've got double bonds alternating like that. And then there would be a hydrogen on each carbon. One consequence of that is that the ring is now flat. Double bonds have 120-degree bond angles, like the corners of a triangle, if the carbon were in the middle. So that means that it no longer does that buckling thing that we saw last week of the 6-membered carbon ring. It's just totally flat. And because of that, it can do something kind of special. Let's draw it as a line structure. We drew those double bonds in that particular way, just because that's how I wrote it down. But we could have drawn it in another way. We could imagine kind of switching these double bonds around like that. And instead making something like this. It looks the exact same. I mean, functionally it is the same, but those are different carbons that now have the double bonds between them. And originally it was thought that maybe this structure kind of switched back and forth, like they were constantly flipping back and forth like that, because one structure isn't any better than the other, and we know electrons can move around. But actually what the structure does is it shares those electrons, those 6 electrons involved in the double bonds are shared all the way around the entire molecule evenly. So one way that that is expressed sometimes is that instead of drawing those double bonds, you just draw a circle like that that shows that those electrons are distributed all the way around the ring. And this molecule, no matter how you draw it, is named benzene. And it is especially stable. So it doesn't react with a whole lot of stuff, although we'll see it does react with some things. The arrangement of these electrons allow it to be particularly stable, and so it's found a lot in nature. It's a really important component. We talked about how 6-membered rings in general, cyclohexanes, are important for biological systems. These come up a lot too, and a lot of different things like common medicines like ibuprofen, drugs like methamphetamine, all have these structures in them. They do a lot of stuff in our body, so it's a common thing. The key thing to remember about benzene, or one thing to remember about benzene, is that it is not cyclohexane. So when you see those double bonds or that circle, this tells you it's a different kind of a compound. It's named differently. It's no longer considered a cyclohexane. So if there were some things on coming off of this, we'd call it 1,3-dimethylbenzene or something instead of cyclohexane. We don't call it cyclohexane. Yeah, it would be cyclohexatriene because of the 3 triple bonds. Yeah, but if we named it that way. But because it's this extra special thing, it gets its own name, benzene. And beyond kind of good things, pharmaceuticals and all that stuff, this is also the source of a lot of carcinogens, a lot of cancer-causing materials. So one thing that happens, I don't know if you know the structure of graphite. Anybody know what graphite looks like? So graphite is a lot of these things hooked together. Kind of makes like a honeycomb structure. And if it's really all connected, like in all directions, there's no hydrogen in there. So because of how it's connected, it kind of takes over. So that's carbon. That's an elemental form of carbon. It's like what's in our pencils. It's sometimes used as a lubricant. Even things like carbon nanotubes or carbon fiber are kind of based on that. Sometimes things are called graphite when they really mean carbon fiber, but that's okay. So that's the kind of structure that the carbon is. So when you burn things, if we remember back to our chemical reactions chapter, when hydrocarbons get combusted, what happens to the carbon? What does it become? CO2. CO2, right. So if you have perfect combustion, all the burned stuff becomes CO2. Have you ever burned wood? Have you ever seen like burning wood or a match? So is it gone when it's done burning? What's there? What's left? Yeah, black stuff, right? That's graphite and carbonized stuff. And that's because when carbon-containing materials burn, they usually don't have enough oxygen because they're not being burned in a pure oxygen environment. They're being burned in air. So they use up the oxygen that's around it, and they burn out eventually. And that what's left is incompletely combusted stuff. And graphite itself is not really bad for you. But what happens is you get these sometimes individual molecules that are like a few of these things hooked together. If there's three, that one's called a terpene. Sometimes they're more honeycomb-y type stuff that have a bunch of them. Those are, or biphenyls, that kind of thing. And these are the products of incomplete combustion that are carcinogens. They get in your body, they cause trouble with your bones and your stomach and your esophagus and things like that. And that's one of the main reasons like smoking causes cancer, is because of these compounds. There's a lot of things, but these types of compounds are a big part of that. Also, cooking meats or vegetables is a carcinogen. I don't know if you knew that. Anytime you get kind of like a nice, delicious, kind of brownish, blackish crust on something that you're going to eat, there's a bunch of those in there. It's not, we don't usually consume enough that it's a problem, but it can be, and it's been mapped that in certain parts, especially 40, 50 or more years ago, when you had much more like local regional foods, certain areas of the country like southeast or northern Minnesota that relied heavily on smoked meats and smoked fishes for food, you saw a much higher incidence of stomach cancers in those areas, and those have been traced to these types of molecules as well. So smoked and grilled type cooked stuff is not great for you from a cancer standpoint. But again, as we've talked about before, it's not like you have to avoid every molecule of these things. It's about the dose that you get and how, yeah.
So what changes it from graphite to that though? It's like a honeycomb shape. Like how many does graphite have to be graphite?
That's a good question. I don't know.
Also.
Yeah, it's a lot. I don't know what it is, but it's a lot. Graphite, you can think of those things going for like thousands and thousands and thousands of molecules. So I don't know what the limit is. But you've probably seen that, if you like cook a piece of meat or something and the edges get really black, you're essentially making graphite or like charcoal on the edges of your stuff. What?
It tastes good.
It tastes good. All right, so that's aromatics. Okay, and then the last thing we're going to look at in this chapter is reactions of alkenes. So up until this point, this organic chemistry stuff has been mostly just about structure. What do these things look like? How do we name them? How do they like flip around? But what's really important about these compounds is that they do reactions. You can react them chemically to form other things. And it's a little bit different from the reactions we've seen so far in that it's a lot more controllable. So when we saw our aqueous reactions before, it was like you take a solution to this, you take a solution to this, you put them together, and they make this thing. But sometimes they don't. But sometimes, we looked at those reaction types and we said, some of these reactions you can predict, some of them you can't. Some of them you can't really tell what it does until you actually try it. Organic reactions, you can look at a molecule and you can say, I want to build this thing. And you can figure out step by step what you have to do to build that molecule. So like just like you do with models, yeah, there. Just like what you do with models, you can say, all right, I want to build this thing, and you could actually physically do it in a lab, and that's what organic chemists do. So they could, let's say, discover some sort of a molecule that has antibiotic properties, but it's also like really poisonous or something. So the chemist might say, well, okay, if we change this part of it and we take off this structure and we put on something else instead, maybe we have something that isn't toxic. And then you actually can make that molecule and then try it. And that's something that's a level of control that we don't really have in other areas of chemistry, to be able to like build the exact molecule that you want to make. And these days, that's even true to like really large, complicated molecules. So we're going to learn some of those reactions and how we can start to think about making one type of a molecule from another type of a molecule. We're going to look at two categories of reactions, hydrogenation and hydration. So for hydrogenation, we're going to take an alkene. Let's start with the simplest one, ethene. And if we are hydrogenating something, what do you think we're reacting it with? Close.
Hydrogen.
Hydrogen, yeah, just the hydrogen part. So hydrogenation is just reaction with hydrogen. And it's called addition. Actually, all these reactions are called addition. So we take our hydrogen, like that, react it with the ethene, and then it doesn't actually do anything until it's introduced to a catalyst, a metal that can help it do its reaction. And the catalysts that we usually use for this process are platinum, palladium, or nickel, depending on the molecule and the circumstances and how much money you have. You pick your catalyst. The hydrogen adds to the catalyst first, and then the alkene also adds down to the catalyst and is reacted with the hydrogen in that way. So when you've done that, what happens is the hydrogen adds across the double bond. And what molecule have we made then from that? Ethane, yeah. So we turned ethene into ethane by hydrogenating it.
So that what that just means like flooding it with hydrogen atoms until it's back to
Yeah, adding hydrogen atoms, one per carbon, turns it from a double bond to a single bond.
So it just breaks the double bond.
Yeah. And this is true with larger molecules. This works with larger molecules as well. So if we took something like cyclohexene, and the way you would write this kind of a reaction usually is you just write the reagents that you use right over the arrow, because we're really only concerned with what's happening to this molecule. It's not like this plus this gives you this. We're more like, we want to know more like what happens to this main big thing. So hydrogen with a palladium catalyst. And when you draw in line structures, it really just looks like you're getting rid of the double bond, but you're actually adding hydrogen. If we count up that molecular formula, this is C6H10, and this is C6H12. So we've added 2 hydrogens in the course of this reaction.
So how exactly do those metals like catalyze the reaction?
It's a solid metal, so it's like a little, well, I mean, it's a powder, but it doesn't dissolve. It stays in solution. And the hydrogen gas is charged into the reactor at a pretty high pressure. And these metals have the ability to bind hydrogen. So the hydrogen binds to the metal surface. And then when the double bond comes in, it also goes down to bind with the metal surface, and that's when it reacts with hydrogen. The metals also facilitate some electron transfer. There's a lot of stuff going on there. This is also technically a reduction when we talk about like oxidation reduction. So there's some of that going on too.
So the metal breaks the double bond, and then the hydrogen attached to it? Attached to the carbons because they have extras, like.
Yeah, you can think about it. You can think about it that way. Yeah.
Because I mean, the
It's
metal's
actually
there afterwards, right?
Yeah, and then so the ethane that's formed no longer reacts with the metal. So once that hydrogen gets on there, it kind of goes away. And it's a single electron process. So there's actually, instead of thinking of the 2 electrons in the bond doing things together, they actually break into single electrons and kind of add hydrogen one at a time. Do you have a question?
Oh, no, I figured it out.
Okay. So the important thing to be able to do, at least in this class for the final with these kinds of reactions, is be able to look at reactants, look at products, and figure out how to get from one to another. So like, which reagents would I use to do this? And you would add the hydrogen and the palladium. Or here's a starting thing, here's a reagent, what does that make? Or here's a product, here's reagents, what kind of a thing would I start with to make that? So basically that last, like one of these reactions, be able to fill in any of those blanks if they were just gone. All right, that's hydrogenation. And then we're going to look at hydration, which is the addition of water. All right, so addition of water, I'm going to draw it a little weird to kind of make it look like what we just did, because they're very similar reactions. So instead of calling it just H2O, which is how we would normally write it, just for this example, I'm going to call it HOH. So this adds just like HH. In this case, instead of a metal catalyst, there are some metals you can do. You use an acid catalyst. And we usually just write that as H plus or H3O plus, hydronium. And that is some acid, some aqueous acid that helps this reaction along. So then we've got the same situation as before. You have what you started with, and then you're adding that new thing, 1 to each carbon. So the hydrogen goes on one side. And in this reaction, we turn ethene into ethanol, which is an alcohol. We haven't talked about the naming of that. We'll get into the functional groups a little bit next week. Yeah,
So is what we're learning right now going to be on the test on Wednesday?
no,
Okay,
this is stuff for the final.
okay. What about like the triple bonds? Because I feel like we
Yeah.
can really just very quickly went over
Okay,
that.
we'll go over it more after. Yeah, we'll go over
Okay.
more in a couple minutes, yeah. All right, so that's that. This can get a little bit more complicated in that we no longer have a symmetrical thing adding to the double bond. So before we had H and H, so it didn't really matter which went where. Here we have H and OH, so if that original alkene is not symmetric, it's going to make a difference. So let me show you a couple examples. Let's go back to line structures and kind of how we would, how we would do this. So we'd say that cyclohexene plus H2O with the acid catalyst is going to make two possible compounds. One is going to be the OH here and the H here. Or we put the OH down here and the H there. So are those compounds the same or not?
Doesn't it just depend where you start numbering it?
Yeah, so they are the same. Like if you flip one over, it's going to be the same as the other one. See that? Or if you even just like rotate it a little bit, it ends up being the same. So those two are the same. And really, since we don't usually show the hydrogen and line structures, we can kind of think of that as not, like we wouldn't have to draw that in. This doesn't belong there. But I wanted to show specifically which parts we're adding across the double bond. So those two molecules are the same. One's just the flipped over version of the other. But let's look at that same reaction with a slightly different molecule. So we add a methyl group on that carbon of the double bond there. Now we make two products. And those are not the same. See how those are not the same? Those are isomers. The OH and the methyl group are either on the same carbon or they're on adjacent carbons. Those are different molecules. So the question then becomes for this reaction, what happens? Do we make a mixture of products or is one favored over the other? In general, reactions where you make a mixture of things are not great because, again, it's all about control, trying to make the molecule that you want. If this were like 50-50 and you made half of one and half of the other, you'd have to just get rid of half of them. You'd have to use some special techniques, separate the molecules out, and you'd lose half of whatever you were doing because half of it was something that you didn't want. So that's not great. We tend to want to use reactions that have a greater what we call selectivity, that only make one kind of a thing. And this reaction actually does. So this particular reaction makes this product and not the other one. Yeah.
The one that you just put the blue around?
Yeah.
Isn't that methyl and a OH?
Yeah.
Okay. And that creates H2O, I don't know.
Oh, the H from the H from the H2O went down here on the other side of the double bond. But because it's a line structure, so this went from having one hydrogen here to having two hydrogens here.
So how do you know to draw the methyl then?
Because that was here in the beginning. It's still there.
Okay.
It just stayed there. Yeah. So you just copy the same structure, but then you're just adding the new thing on. So in general, with this reaction, the OH goes to the what we call more substituted carbon, which means that carbon is connected to more other carbons. So substituted for hydrogen. So if you're looking at something like this and you want to decide where does that OH go, you say, okay, this carbon has 3 carbons that it's connected to. This one has 2 that it's connected to. So the OH is going to go on this one because it's connected to more other carbons. And that's what we see here. So let's try that. So what's the major product of that reaction? See if you can draw that based on what we just saw. So think about this the same way. We've got 2 carbons in the double bond. One gets the H and one gets the OH. The OH is going to go on the carbon that has more carbons connected to it. So which one is that? The one in the middle or the one on the end? Middle, right. So the product should be that.
You don't have to write out the extra hydrogen.
You don't. As long as you kind of keep it in your brain that it's there,
Okay.
you know that it's there. If you're using line structures, you don't have to. If you're using condensed structures, you do. All right, so those were the reactions. So let's see how well you can do with these. Grab your practice quiz again, look at the back side, and see if you can fill in the blanks for these 3 reactions. And we'll look at it.
What kind of a structure has to be able to start with? Yeah. Right. So decide where that's going to go. Right. Yeah, so is that right? Yes.
Is that because the ones that don't have the double bond are already filled with hydrogen?
Right, yeah. Alkanes are relatively unreactive. They don't react with water in the same way. So you need the double bond to be able to do the reaction. All right, looked like most people took a shot at it. So let's take a look. So in the first one, we're adding hydrogen across the double bond, which means we're going to have 2 extra hydrogens, one on each carbon of that double bond. In line structure form, that just means the double bond kind of goes away because we're turning an alkene into an alkane. So the product should look like this. Same thing, but there's no longer a double bond there because there's extra hydrogen. Instead of having 1 hydrogen here and no hydrogens here, we have 2 here and 1 here to make 4 total bonds on each carbon. A good thing to remember for all of these, just in this class, it's not true for organic chemistry in general, but in this class, is we're not ever getting rid of anything in these reactions. So whatever starts the reaction, that whole molecule is still going to be there at the end. The only thing that changes is the double bond is going to go away and something else is going to end up there instead. So in this next one, it's kind of asking the opposite thing. What do we have to start with to make that product? And you have to start with the answer is some kind of a double bond. So where does that double bond go? Well, it has to go somewhere. It has to go in the right place so that the OH can end up there at the end. And there's actually 3 correct answers to this one because it's an asymmetric structure. Actually, there's more if we include cis and trans. That's one. That also works. As does that. And then there's actually 2 more. There's I'm guessing probably nobody picked these. But there's the flipped version of that because double bonds don't rotate. And then there's also the flipped version of the first one.
This one loses me.
I mean, don't worry about it too much. As long as you got one of those.
As long as it's.
Okay, you didn't.
I
Okay.
don't get why I'm doing it. Like, I don't get how the OH appears and the bond breaks.
All right. So let's see. We start with the double bond. Let's just take this one. If that's the thing that we started with, we have to add water to that double bond, which means the H goes on one side and the OH goes to the other side. So if the H goes over here, then we have a carbon with 2 hydrogens on it because it already has 1. So we add 1 more H, and we have a carbon with 2 hydrogens, 1, 2. Then this carbon gets the OH, which shows up right here. There can't be a double bond any longer because those are the electrons that are used to make those new bonds, and you can't have more than 4 bonds to the carbon. So. Yeah.
That's the water. It's the same thing. H-OH, whatever.
Okay, so you just have to add an H and an O.
Yeah, because water is H and OH. Okay. I mean, it takes practice just like anything else. We just saw it, so it might take some time to work through it a little bit. So for the last one, we're now adding the water. So that means we're going to add the H to one side, the OH to the other. And the question is which goes to which side? So what do you think? Or what did you?
OH goes to.
Yeah. The one with the extra thing on it, right? Yeah, because when it's asymmetric like this, we have to put, so the OH is going to end up here, and the H is going to end up here. And that makes a structure that looks like this. All right, so work on that homework when you get a chance after Wednesday, because this stuff is not on the exam on Wednesday. So you can just push it all out of your brain right now. And let's focus back on the stuff that is on the exam on Wednesday. So what do you want to go over? I already heard a request for alkynes, triple bonds,
The chapter 5, so I'm curious with that.
the nuclear stuff.
Yeah, the nuclear stuff.
Okay. Anything in particular that's been giving you trouble in the homework? Okay. All right, let's take a look at alkynes again first. So the only thing that will come up with those is in naming, naming structures and then like molecular formulas. So let's look at something like this. So can you name and give the molecular formula of this structure that includes a triple bond?
Since there's a triple bond, is there, 6 carbon, is that a 6 carbon chain or is that?
Yes, because the triple bond doesn't bend. So each end of the triple bond is a carbon.
So is the 3 bound the alkyne?
Yes.
For a double bond, it's hexene, so what's a triple bond?
Hexine with a Y. Yeah, this is kind of open review time now, so we're not going to take an official break, but if you need a break, of course, take a break.
Can you start numbering on either end, or do you start numbering what a triple bond would be?
At the end closest to the triple bond. So you have to start from the end, but yeah, in this case, you want to start from the left end because that's where the triple bond is closest to. So that's what your numbering should look like.
formula is just like the C and the H, right?
Right. Yeah. How many C's and how many H's? All right, so we got a name? Close. Close.
2. Oh, sorry.
So it is 5-methyl, is the methyl group there. But then we have to specify where that triple bond is, because it could be at the end, it could be there, it could be at the next carbon over. So we have to say where it is. So it's 2, yeah. So we can either write that as 2 hexyne or whoops, or we can put that in the end. I don't remember which they say in the book, but either is okay.
It's that one.
It's the second one? Okay, we'll stick to that then.
Second one.
I think so.
I feel like that was more confusing.
I think it's because the 2 is like directly next to the ion part, because it's saying where the ion is instead of being in front here where you have to kind of decide what that applies to. They're used interchangeably in practice.
So either one would be correct on the test then.
Yeah, right.
I almost started numbering it at like the 3 as the 1 because you said that it had to be the lowest, and I keep getting hung up.
Yeah,
You
it's
gotta start with
you
1.
always got to start at the end,
Okay.
but you want the double or triple bond to be closest to that end that you start on. So what's the formula here? Not the condensed structure, just like the molecular formula.
H12.
No, it should be C7H12.
Yeah.
C7H12. Right? 1, 2, 3, 4, 5, 6, 7 carbons. Hydrogens are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
What's another one?
All right. Get another one.
Is it
No, that's not nice. Let's see. Let's try this one. So similar with one little extra thing. See if you can figure out, we didn't really talk about how to do this. See if based on the rules, if you can figure out how this one should go.
Seven is hep.
Yep.
heptide.
Right, 1, 2, 3, 4, 5. But I don't think you need that in this case, do you? 1, 2, 3, 4, 5. Oh yeah, you do. 6, 7. Yeah, hept. H-E-P-T. Yeah.
I think it doesn't matter.
I think you usually put the ion last, but it doesn't really matter.
Did you put 6-methyl and then 2 ion?
Yeah,
FD?
right. So you'd go,
You put iron in,
yeah,
that's what I figured.
Yeah.
Okay.
so that's how you do it. So you'd go 6 methyl hept 4 ene 2 ion.
Would it also be acceptable to do 6-methyl 4-heptene 2-heptine?
Yeah, I mean, I would accept it. You know, it's redundant because you have the hept twice,
Right.
but yeah, I think it's still a unique name, right? It still shows what it is supposed to be. Same thing if you switch the ene and the ion, or if you put heptene, or if you put like 4-heptene 2 ion or something like that, I would be fine with that too.
Yeah, so 6-2 ion, and then.
As long as you get the ene in there too somewhere, the 4 ene, because there's a double bond on 4. All right, so let's take a look at Blackboard. For chapter 5. All right, so there's not a whole lot here. Definitions is not really an important, I mean, we haven't really seen it much on the exams. I wouldn't worry too much about that. Types of radiation, ionizing radiation, sure. Nuclear equations will be the big part of that. So like if it's alpha or beta decay, how do you draw that equation?
Wait, which one did you say don't worry about?
Number 1,
Number 1.
I mean, you probably know what those things are just from what we've talked about. And then the main things will be number 5, balancing the nuclear equation, writing the balanced nuclear equations. And number 7, calculate stuff about half-lives as you did in that lab and then in the practice as well. And we did a quiz on that too. What is nuclear fission? What is nuclear fusion? You don't have to have those equations in like memorized, but be able to recognize them, know what they are. They do. Yeah.
And what chapters is this exam on? 5 and 11.
5, 10, and 11. But technically it's cumulative everything. I mean,
But those are the new ones.
5 and 11 are pretty separate. I mean, there's really nothing from old stuff that goes in with that because they're really, really different. With the acids and bases chapter, because that's still dealing with things like concentrations, equations, all of that, we'll bring in some of the old stuff, some of the naming, some of the stuff about molarity. So maybe brush up on that stuff as well. Some of the solution chemistry from chapter 9, and then the equations like neutralization reactions. I don't know, it doesn't say that specifically here, but be able to write a neutralization reaction like we had in that quiz, and is in the homework as well.
we do some problems doing that?
Sure. All right, so here's one. Nitric acid is neutralized by calcium hydroxide. Write the equation, write a balanced chemical equation for that. All right, got some reactions? Maybe? So that's another thing to point out in here. Make sure you know what these acids are and bases. I mean, the bases are not a big deal because you should know how to write ionic compounds anyway. But the acids, make sure you know the formulas because it can mess up your equations and stuff if you don't. Yeah.
You do just
Well, what's it?
like NO3 through an H to make nitrate, and then
Yeah.
it says you put hydro in front and egg at the end, but
That's only for the halogen ones.
Okay.
Yeah. Because it's like sulfuric acid. Yes, you throw an H in front of sulfate, but you need two H's
yeah, you have
to balance the -2 charge. Yep. Okay, so neutralized by calcium hydroxide. Calcium hydroxide is CaOH2. And if it's neutralized, what is the product? H2O and something. So what's the something?
Calcium nitrate.
Yeah, calcium nitrate. So it's really just a double replacement reaction. The H goes with the OH. H plus OH is water. So then the other two go together also, calcium and nitrate. And we have to adjust the ratios to make sure the charge is balanced just like in any other compound. All right, so then we got to balance it. So that's 2 of these and 2 of these. But the key to doing this, I mean, besides knowing the formulas of the starting materials, is recognizing that neutralized means forming water.
Why was there 2 nitrates on the right side?
Because calcium is +2 and nitrate is -1.
Okay.
So to build the compound from those, you need 2 nitrates for each calcium. What else?
Another one of those.
Same thing. Let's look at what happens when we use sulfuric acid.
So would sulfuric acid be HSO4,
Close.
SO3?
It's H2SO4 because sulfate is -2. So you need 2 + 1 hydrogens to balance that formula.
Those numbers in parentheses, that's depicting the charge.
The charge on iron, right?
What's the iron?
But,
What's the,
oh, Fe. Iron is Fe.
OH has a -1 charge.
Right.
So it'd be parentheses OH3. On the right side of the equation, would it be H2O plus 2 FeSO4 3?
Well, let's see how it balances out. So you've got H2SO4 for sulfuric acid, iron hydroxide, iron 3 hydroxide. It's a neutralization reaction, which means we form water, and what's left, which is iron 3 sulfate. So that's Fe2 SO4, 3. Okay, so then we have to balance this. We're going to need 2 of these, 2 of these.
You do that about.
Oh, that doesn't work. So we got to have 3 of these first, right? And then, or 6 of those, you're right.
No, 6 of the H2Os.
Oh, yeah, okay.
6 water.
Yeah, yes, we just change it, multiply everything by 3. No, 2.
You were good there, yeah.
Nope, that doesn't work. Does it?
Is
Oh, yeah, it does. Yeah, yeah. Yeah. Sorry. Okay, so that's the balanced equation. What about pH? Feel good about pH? Do some pH. Okay. All right, so 2 different situations. Those are 2 different situations. 2 different solutions. One where the hydronium ion is 1 times 10 to the minus 9 molar, and one where the hydroxide ion concentration is 0.001 molar. So what's the pH of each of those?
For the first one,
Yeah.
to add up to 14, right?
Right. For the second one, you mean?
For the first one, like the next one, that's the 14.
Well, these 2, the pH, which is based on this, and the pOH, which is based on this, have to add up to 14. But if you already have this concentration, then it's just that to get the pH. So for this one, the pH is 9.
So
The other one's 3.
the other one is not 3.
The other one is also 9.
It's also not. What is it? Is it 9?
Is that
How do you know
one?
it's
Not 9.
Negative.
Sorry,
Yeah, would it be 11?
11. Because I'm apparently not capable of doing
How do you get that?
subtraction today.
The 9.
All right, let's look at this. So the pH is, if you remember, is the negative log of the hydronium ion concentration. So if the concentration is 1 times 10 to the minus 9, the negative log of that is 9. If you're given the hydroxide ion concentration instead, you can calculate the pOH, which is the negative log of the hydroxide ion concentration. And then you could subtract from 14 to get the pH. So in that case, 0.001 is 10 to the minus 3. So the negative log of that is going to be 3. And then 14 minus 3 is 11.
What's H3O again?
Hydronium. That's what happens when acid is in water. And the H plus goes from the acid to the water molecule.
Would it ever be represented just as like just a hydrogen?
Yes, sometimes it's listed as just the H plus. In this class, like in the exams and stuff, I don't think you would see that because we've always done it this way. That's where it comes from, is it used to always be done the other way, but it is more realistic to do it this way because there are no free H pluses in solution. They're all bound to water. So it makes more sense to talk about that as hydronium. Outside of this class, you might see it that way.
Yeah, I've seen it before.
Yeah.
I've never seen that before. So-
Okay.
What if you're given the H3O, that's the
Hydronium
hydronium?
Yep.
And it asks you.
for the OH.
Yeah.
Then you've got to subtract from 14.
Oh.
Okay, so you use this equation. These two added together, the pH and the POH, always equal 14. So what else? Yeah,
Can we touch on some nuclear chemistry?
nuclear chemistry, sure. Let me pull some of these up because I don't know a lot of these like just offhand. Or I guess let's pull them out of the book because that's where I get a lot of the stuff for the exam anyway.
Wait a minute. This is weird. Because, yeah.
All right. Here's some examples. Oops. All right, so I'll do one and then try a couple. Write balanced nuclear equation for the alpha decay of each of the following radioactive isotopes. So let's take this one, benzstinium. So if it's alpha decay, you know the particle that's coming off of it is an alpha particle, which is that, yeah. And so what's left over then is what is left over. So how it works out, 99, if you want 99 total, that's 2 and 97. If you want 252, that's 4 and 248. So then you look up on the periodic table, 97 is berkelium, BK, Burger Kingium, yep. Pretty sure that's what it is.
What is it really?
Berkelium. We can just call it Burger Kingium too. And W is Wendysium. I don't know, what other ones?
So you just take the.
There isn't an MC. There's PO for Popeyesium.
You just take the bottom number and put that.
Yeah,
And find it on the periodic table.
yeah.
There's MD.
Yeah. It's like the McDonald'sium.
But the alpha always is gonna make 4 or a 2 on the bottom.
Right. That's an alpha particle. It's a helium nucleus. Yeah.
So the top number is the mass number, and the bottom number is the atomic number.
Right. Yep. So then if it's beta decay,
0 minus 1.
yeah. So a beta particle is an electron, which has an atomic number of -1. It's like a charge of -1 and a mass of 0. So then the other numbers are 9 and 20, and that's fluorine.
So the alpha decay to 4-2, yeah, and the beta, it's the loss of the electron. And the gaining of the proton.
Right. And then don't be fooled if these are written this way. Strontium 92. You can look up the atomic number on the periodic table, it's 38, and still do the rest of it the same way. The bottom number is redundant because the bottom number defines the element. So if you know what the symbol is, you know what the bottom number is, vice versa. All right, what else do you want to do? Are you working on the rest of those? Okay, that's fine.
And then for delta decay, it just becomes stable. It just, you can do the 0.
You mean gamma?
0. Or yeah, gamma.
Yeah.
Sorry.
Yes, right. So it goes from metastable to stable. So there's not really much to do there. The numbers don't change at all.
So do we need to know about gamma ray reactions then?
Yeah, I mean, you don't need to know about them.
You just use.
But it's nothing, it's like, it's just losing energy. So the equation doesn't really tell us a whole lot. Because nothing really changes. It just goes from a less stable to a more stable state as it loses its energy. So know that that's called gamma decay, and that's a gamma decay reaction. That's a gamma particle, but there's not much else to do there. So what else should we talk about?
Just went to Turkey Day.
How did I? I made some turkey,
Nice.
then I ate it in the company of family. It was pretty standard, I think. How about you?
Yeah, likewise.
We were actually in California last week.
Oh,
Actually, before I forget, can we turn in our lab 12 stuff?
yes.
Okay.